Now let's have a look at the third part, the landmark update. So now the situation is as follows. A robot makes a measurement, identifies a cylinder at a certain range and bearing angle, and there's an existing cylinder, some covariance matrix, and after computing the likelihoods, we decide that this measurement belongs to that landmark. And so we want to update this landmark. So if this is our old position of the landmark, say mu old, and this is the arrow ellipse belonging to our old covariance matrix, then we would now expect that due to our measurement, the position of the landmark will move here, so close to the measurement, and as a result of this additional information, the arrow ellipse will get smaller. So this will be our new mu, and this will be our new covariance matrix. Now remember, each of those landmarks is a separate extended Kalman filter, and so in order to figure out how we have to update the position of the landmark, we'll just have to write down the standard Kalman filter equations. So in order to update the state, we'll first have to compute the Kalman gain, which is the sigma, namely the old sigma, times the Jacobian of the measurement function transposed times this term. Now this is just copied from our standard equations, which we have repeated by now for multiple times, but now you understand what this term means, because we derived this just a few slides ago. This is the measurement noise due to the noise of our measurement device, and this is the measurement noise that results from the noise of our landmark propagated through our measurement. And so we just computed this, and this was QL. So this means our K equals sigma old times the transposed of T times the inverse of QL. And from that we can compute our new mu, which is our old mu, plus the Kalman gain times our measurement. So this is our actual measurement minus our expected measurement, which is computed by the h function given the state and our landmark position. And our new covariance is computed by this standard formula. So it's the identity matrix minus Kalman gain times h times our old covariance matrix. This is all there's to do. Now for the practical implementation, remember that h and ql are computed by a function you've written earlier, termed h, ql, Jacobian and measurement covariance for landmark. And h, function, is computed using h expected measurement for landmark. And so you know everything you need to know. You know h, you know ql from this function. Sigma old is the old covariance in the particle. C is given to the function as a parameter, h is computed using this function, k is just computed here, and the mu old is also taken from the current particle. And everything else here is known as well. So I prepared this LAM10D update landmark file for you, and it contains, as usual, the particle class. Now this time I included the measurement function h, and the derivative with respect to a landmark. And you will also need the expected measurement for a landmark function and the Jacobian and measurement covariance function, which you programmed earlier. So just copy your code here. And here the update landmark, that is actually the new code that you'll have to program. Now looking at the previous slides, that's not very hard to do. And here are some additional hints, which you'll hopefully find useful. Now the main code checks your implementation. So it sets up a particle, it inserts some landmarks, and those landmarks are actually the ones which result from our initialized new landmark code in the previous SLAM10C programming exercise. So the three positions of the landmarks and the three covariance matrices are just inserted into the particle here. And so after we inserted those landmarks, we print them, and then we update our first landmark, so landmark number 0, using this measurement that is a range of 1000 and a bearing angle of 0. And please note, in this case, we set the correspondence of the measurement to landmark 0 manually. So later on, we'll have to replace this by the code that assigns this measurement to the landmark with the maximum likelihood. So here, we measure the first landmark once again at exactly the correct location. And then we measure the second landmark once again with a location that is slightly different from its previous location, namely its x value is larger by 100 millimeters. And we don't update the third landmark, and then we print out all landmarks again. And so if you run that, you should see this. With our first landmark at 1000, 0, with an error ellipse like that. Our second landmark at 2000 with an error ellipse the same size in the x dimension, but twice the size in the y dimension. And we have a third landmark, which actually is here. Now look at the update. The first landmark is updated with exactly the same coordinate, so it stays in the same place. But the error ellipse gets smaller in x and y. If you look at this should look familiar. So and this is 200 divided by the square root of 2, which happens to be 100 times the square root of 2. And also the second half axis is this 261 divided by square root of 2. So I measured this landmark 2 times, which means that the variance is 1/2 of the variance after a single measurement, which means that the standard deviation is the standard deviation of a single measurement divided by the square root of 2. So this gets smaller by a factor of square root of 2. Now look at the second error ellipse. The very same happens here. So the error ellipse gets smaller by the factor of square root of 2. But in this case also the position is different. Now because we did our measurement here at 2100, the resulting position of 2 measurements with identical accuracies is exactly in between. So here this will be 2050. And around this we will have our error ellipse, which is smaller by a factor of square root of 2. So we observed this earlier, that the variance behaves exactly the same as in this case, even though here we didn't move, but here we moved. So once again we see that the computation of the estimated mean value and the computation of the estimated variance are independent. So if we had measured a range of 2000, then the position would stay 2000 and we would get exactly the same result for the covariance matrix. So now please program this and check your result against this outcome.